Check sound. Tes. Ladies and gentlemen, welcome to the ICE Technical Meeting, Geotechnical Investigations and Studies Relevant for Existing Dams Safety in Indonesia and Worldwide. This event is brought to you by the Institution of Civil Engineers and supported by Multibangun. My name is Rifa, and it is a pleasure to act as your master ceremony in this event. Before we start, allow me to read the rundown of our event this evening. First, I will be reading the rules of the webinar. Second, there will be opening and closing remarks by the representative of ICE-JLA Local Association, David Mee. And after that, our speaker, Edward Flint, will start the presentation. Ladies and gentlemen, for your own convenience, please put attention to the following rules. You can submit your questions for the online attendees through the Q&A feature located at the bottom of your screen. The question should be in English. If you are here with us in Kemang, you can just simply raise your hand on the Q&A session later. You can raise your questions before, during, and after the presentation of the speaker if you are joining online. Now, I would like to invite the representative of ICE-JLA Local Association, David Mee, to give his opening remarks. To David Mee, the time is yours.
Okay, ladies and gentlemen, welcome. I have to apologize for not being with you. I'm actually in the UK. It's just at 12 o'clock midday here. About 6 months ago, when I was working in Bangkok on the flood management project, my team leader told me about his mentor called Ed Flint that was also in Jakarta, and he asked me to get in touch with Ed. So I invited Ed to one of our meetings where I found out he was a dam safety expert. So I'll just tell you a little about Ed, although you probably know already from the invite. Ed graduated from the University of Washington in the US in geological science and went on to do an MSc in geotechnical and photogrammic engineering. He spent 20 years with the US Corps of Engineers. They're the guy, along with the USBR, that write a lot of our design guidelines. So that comes as a very strong recommendation. He was concerned with safety aspects of dam and levee engineering. He's worked in a range of countries. I'm not going to list them because you've probably already read about them. But included a lot of work on risk assessment and decision making regarding large dams. And this brought him to Jakarta as well, even though it doesn't seem to him mentioned on his CV. He's probably been to a lot of other countries as well. So I was very pleased to meet Ed, and I asked him, and without reservation, he agreed to give a talk when we could arrange it, preferably before he might have to leave Indonesia. As a water resource specialist, I've always been on the fringe of looking at large dams. One of my earlier projects was installing geotechnical equipment and calibrating it and commissioning it in a dam in North Wales. At the time, there was a talk by the Institution of Civil Engineers in the Northwestern region on the safety of the Grand Teton Dam in the US. So I joined that talk and listened to the details of its disaster, which I think Ed will give us some background on during his talk. At the time, while I was commissioning dam safety equipment, I asked them, well, what happened? You're the guys that write the design manuals. Why wasn't the equipment in the dam going to tell you it's about to burst? For which they said they didn't think that would have helped, but I differed. Anyway, perhaps Ed will give us some insight into that. So I'm very pleased to introduce Ed, and hope you enjoy his what looks to be a very interesting talk on dam safety. Recently, the government of Indonesia has confirmed that it wishes to build 54 large dams in Indonesia, of which something like 36 are already in construction or completed. So this is a very critical talk for Indonesia and anyone who's going to become a dam engineer here. So I'd like to now hand over to Ed and hope that you enjoy his very interesting presentation. Rifa?
Okay, ladies and gentlemen, please welcome Ed Flint.
Good evening, everybody. And there's a camera there. Thank you very much. And David, thank you very much for your maybe too much glory. Okay. There might be a small delay, right? Okay. Yeah. All right. Can we open the first page? Yeah. First slide. Yeah. There we go. Okay. Yeah. And this, we're going to distribute this presentation to everybody as we can, so that because there's a lot of good notes in here, good references that will be very helpful in understanding the whole issue of dam safety from the start. And that's what I really want to go over. Can I just hit the down arrow, right? Oops. I want the next slide. Oh, just a minute here. Not my computer. Okay, all right. Okay, what we're going to talk about this afternoon, and I'll go through some of this a little bit quick. There are some good videos in here. If we have time, I'd like you to see some of these because they're recorded dam disasters and or put together dam disaster videos that I got on YouTube. But the purpose and objective, why are we here? What are we going to do when we're here? We're going to give you the definition of large dam by the World Bank, sources of data. And let me just get into the next one. And we're going to want to show you some of the requirements to understand the geotechnical investigations and studies for safe. Not just geotechnical, every aspect of engineering is in here. And I encourage all you civil engineers out there to really take advantage of any volunteer, get a job working on a dam, and you see that it's not easy. And there's many things that have to go on. If you're working for a geotechnical or foundation engineering, you're going to have some really good work. I spent the first 2 years in the Corps of Engineers in the field behind a drill rig, sampling, taking soil samples in the cold water, someplace snow, Martis Creek near Lake Tahoe. I worked up there in the winter time, trying to do investigations on that. We're doing a test fill of the dam. So there's all kinds. So these reports are important. And as you'll see, there's some examples. I have some examples of poor geotechnical report where the geotechnical company didn't look at all the stuff. And you'll see in some of the dam disasters what's going on. And what are we going to do inside these reports? What do we want inside? What is the most important thing? There's so many. I'm a member of the USSD, United States Society of Dams, and also American Society of Dam Owners. And so many things can go wrong. That's why when you sign off, if you're a professional engineer, you sign off, you're not responsible. And as you'll see about one of the Italian dam, the guy went to jail for manslaughter. But here, and the comic down below, this is from the old comic, this is an engineer. Okay, how do we get the electricity from nuclear power to the toasters over here? And it talks about it. And people don't understand how you have to transmit hydropower to the homes. So it's quite interesting how you get the power there. So even the solar and the wind power that they're pushing now, what do you do when there's no wind? You have no power. You have solar power, no sun, no power. There's no storage yet. And the cost for that is phenomenal. So I'm a renewable resource person, like water. Water is your best answer. So, and international, any dam higher than 15 meters. And usually there's a risk if the dam is a long dam, risk go up. If it's a short dam, like in a small narrow canyon, risk go down. But a large dam is anything 15 meters or higher. But small dams, 5 meters or 15 feet, like I worked on the levees in California during 97 and 98 floods, they're 12, 16 meter high levees. And we had 29 levee breaks. So, big problems with levees. Same as a dam. I want you to remember this. When you have data and you're looking at data, even in your textbooks or whatever you find, you have a little bit of data, a lot of opinions and a lot of assumptions. You just look on LinkedIn, you'll see, and that should be just the opposite. When you make a decision, have good data. Don't have poor data. Make sure you answered all those hard questions that, did we look over there? You know, as I'm a geologist, my bachelor's in geology, I'm licensed. But how far apart do we space the borings? 5 meters, 10 meters, 1 meter? No, maybe 50 meters to start with. If we find something, that was in the days before geophysical investigation. So what I've done now is, in India, I use this procedure. We hired a geophysicist company, and they first scanned the dam. So when we did borings, we know where to drill to back up for ground truth. Very helpful. So that's what I just want to make sure this gets clear, is that we want very few assumptions. Okay? Don't go by textbook. Textbook will never describe. I was working on Cheruiyot Dam, Cheviot Dam out here till January, and we found all kinds of interesting things in the foundation. So we'll get into that. Foundation and piping are some of the issues you have. I have a video here, but I'm not sure if we have time to show it. I don't know. I don't know how much time we have. Is somebody going to clock watch for me? So, but But this one, this is about foundation and piping failures. Yeah. Mhm. Mhm. Whoop. What do you want? Whoop. No, yeah, yeah. I already had it. I just click it on my presentation. Yeah, here. Control, yeah. Oh, yeah, okay, all right. Okay, yeah, okay, this is the foundation. I want you to listen to this.
Calamity almost beyond imagining afflicts Frejus and nearby Sao Rafael. Inland from the sea, acres of water, mud and wreckage sprawl over the area. Desolation on this scale stretches for 8 miles up the valley of the River Rayronde, where the shattered Malpase Dam marks the starting place of the disaster. It was a new dam. Only the day before had the impounded lake, 5 miles long, been filled to capacity. And only 3 hours before it burst, did apprehensive engineers partly open the floodgates.
Oop, unstable. Sorry, the internet's a little bit unstable. Huh? No, that's okay. You go back to my presentation. Yeah, hit play. Yeah. Okay, what happened here is that this dam was just filled the day before, like many dams. If you want to talk about dam failures, oh, what's this? Oh, oh, oh. Can you hear me? Connected, yeah. Oh, okay. Oh. Yeah. Good play, good play. There we go. Oh. Back up, back up, back up. There we go. Okay, what happened here after the test failed? What they didn't do, they didn't realize that there was some problems with the foundation on the abutment. And when they filled it, guess what happened? Hydrostatic pressure. And she loosened the rocks, down it came. Okay, it just collapsed. You'll see that so many times when you look at dam disasters. What happened? Not from overtopping. That's about 38%, I think, 35%, but from foundation problems. So it's important that when you study foundation, and they were warned, there's actually a discussion on that. If you look at the literature, that they said, but money, time, let's get it built, go on, move on. So then the Vahant Dam in Italy, that was to me, I just can't imagine that you would have a wall of water rise up when the whole reservoir filled with soil in a few seconds. That wall of water came over the top of a wave 250 meters high. I can't imagine. They didn't have cameras there, but it would have been scary. Okay, and it killed so many people. They've never recovered many of the bodies. That's called a mega tsunami. that term was new to me till a couple of years ago. I'm going, mega tsunami. I was here in 2005 after the tsunami hit Sumatra. I think tsunami. This is from a landslide where the whole left embankment came down into, left embankment came down into the reservoir, displaced all the water at one time. Unbelievable. And this one, I've been studying this one for a long time. I use this one in dam safety training. And this was a hydraulic filled dam. If you know what that means, you build your two clay embankment, then in the middle you pump in sand and the water drains out. Okay, so they pump in the stuff and then let it settle. You see the orange, I don't have a pointer here, but the orange center is all fill. I mean, it's and it was, so it had a 6 point, I can't remember now. It had an earthquake. One had two control towers. This supplied water to the city of Los Angeles. And at that time, the record, if you look at it, it said 80,000, but then it was updated to 120,000 people lived right down the hill from this dam. They almost lost it. Almost lost it. They came within a couple feet of overtopping. If it had started overtopping, she would have completely eroded away. So this is where in the early 1900s, Teddy Roosevelt, they authorized the Bureau of Reclamation to build an aqueduct from the mountains, a place called Apple Valley, to Los Angeles. And they, okay, you can hear me. Oh, I'm sorry. Not a big audience here. But anyway, they built this aqueduct. So this was the end of the aqueduct. And there's a dam now today, it liquefaction. This was failure by liquefaction. Seismic activity, liquefied, she just collapsed. Very luckily, it didn't overtop. They did evacuate the people, but it wouldn't have been enough time. Seepage and path, and you heard David talk about Teton Dam. This was the first one that I've actually been to this dam. There's no dam anymore. It's a park area now in Idaho. I used to go fishing over in that area, Idaho, on the Snake River. And this dam failed. Again, they noticed seepage downstream. They were doing a test fill almost to the top. And they started seepage downstream and it worked its way up until you saw the erosion on the lower part of the dam and then on the upper part on the right bank, right abutment. And she just collapsed. And my mentor in the Corps of Engineers, Mr. Clark Stanage, branch chief, he was involved in that, looking at that after it collapsed. He's an old-time Corps. And because of the Corps dam. The sister dam to this upstream doesn't leak 1 liter of water. Same design. Well, what happened here? If you're this part of the U.S. has got lava plains, vesicular basalt, lots of holes in it, in the upper area, and it allowed water to come through. They found caverns inside on the right abutment, 8 feet or almost 3 meters in diameter. They didn't grout the cavities. So water entered into the core, collapsed, and the core was made, usually when you build a embankment dam, you have to watch out your materials, but it had some silt in it also. And that silt was very erodible. You can see here, they lost 2 dozers. And in that day, no instrumentation on the dam, no radio, nobody there, except the on-site operators. And there was 2 tourists at an overlook. And the tourists said, hey, dam's breaking. These pictures came from a tourist. Yeah, not somebody at the dam. So what happened is they rushed downstream yelling and honking horn, telling you, get out, get out, get out. 16 people were killed, but it did do a lot of damage. It flooded two towns downstream. It's a good video on here. I want you to watch that. Another hydraulic failure. I've been to this dam. It's in California in the Central Valley up near Chico, California. And it empties into the Feather River. It's the highest embankment dam in the United States, 700 some odd feet tall. And what happened is that the spillway, even though it goes through a annual and a 5-year evaluation for dam safety, the inspectors did not look at the drainage in the spillway. Uh-oh. And what they found out, the drains were plugged. So the drains were not open. So what happened is, as the water level raised with unbelievable rain in 2017, it filled this dam to the top. First time it spilled in many years. And even the emergency spillway over top, emergency spillways 300 meters long, 300 meters. So everything went, you can see on that top right, you can see the first, they said, hey, why are those bubbles coming up? So they stopped it, they closed the gates temporarily, and they saw, oh, the spillway's gone. It collapsed, washed away, floated downstream, hydrostatic pressure. So they said, oh my God, you can see the erosion on the bottom left, how much it eroded before they finally got it under control. They got the lake level down low enough to allow it. They had to. That dam would have broke 700 feet high. My God, all Central Valley would have been flooded. I was there in Central Valley during the 97 and 98 floods, and we had a flood fight, two embankment dams there. So just because of the sand boils at the toe. So all kinds of interesting but scary stuff. And so what I'd like the students to take away with this is, that's why I want to make sure this is available to them, so that they can look at all this and say, how does this pertain to what I want? We have any geotechnical engineers here? Soil mechanics? You? Yeah, good. All right, you can answer the questions. Yeah. Okay. We have structural engineers. We're just looking at backgrounds. Structural? Yeah. Okay. Civil, yes. Okay, all right. But I want you to just understand that it's not easy. And if you are responsible for a dam, you have to understand the responsibilities. You don't fudge, you don't cheat. Terzaghi said one time, I love that guy. I didn't study, I'm not that old. I didn't study under him, okay? But I understand, I studied under one of his grandson, they're called Michael Duncan, Dr. Michael Duncan. He ran Berkeley for a long time, then moved to Virginia, where he got a better deal than California. Anyway, I took graduate school courses from him. Really nice, really nice. And he said, Terzaghi said, if you make a mistake, don't hide it. You say, I made a mistake. Okay? And he got fired from Union Pacific one time because he had given instructions on the trains running rock during the 86 flood out of the Bay of San Francisco. And he said, tell the train locomotives, don't no faster than about 10 kilometers per hour. That's as fast as you can go on these tracks, because the levees, the railroads are soft. Okay, they're saturated. And the two trains were, the first one to get there gets a prize, gets more money. And they were speeding. And at 2 o'clock in the morning, Dr. Duncan got a phone call from UP, you're fired. Why? We lost 2 locomotives. They were going 60 kilometers an hour, and it vibrated, it shook the levee like liquefaction, collapse. 2 locomotives. He said, don't be afraid, to be honest. Make a mistake. But he said, it wasn't my mistake, but I got fired. So good idea. And then I think that also for the students, I'd like you to, if you haven't considered this as a field to go into, it's an important field. Especially here in Indonesia, where you have so many natural problems, tsunamis, earthquakes, volcanics, okay, all kinds of things that are not good, okay? And you got a lot of dams. And I think I want to just I think there were 60 dams when I was working at the under the World Bank program here. There were 60 dams. I think they finished some of them. I don't know how many are left, but all these dams need to have more people going out in the field and study them. Okay, we'll get around to that. I just like you to understand that when you read through I have lots of notes in here and references. They'll be good for you. Maybe you can PDF it and send it by PDF. Also, that'd be good. Okay, just PDF the notes. Be good for everybody to see. It took a while to do this. And then, so where do we get our data? This is another problem that we ran into in India. I was in India for 5 years. And one of the biggest problems was, where's the data? Oh my God, they have some dams that are 1,000 years old. They don't have data. Okay, they're still actually good, but they have some dams that are newer that have problems. But where are the field reports? So we set up and now you have it here also, a database at their ministry where if you could log in and get all the data, all the annual reports, the flood reports, all the data. I think here you have it on Dam Center. I was going to link that up, but I don't have access to it now. There's a link here at the Dam Center, and you can go in and inspect, look at every dam and see what its condition is. You also have another book here. I'll talk about it a little bit later. But construction inspection reports. India, we had trouble finding a lot of construction problems, and I know when we were working under DOISP, at come on, but another dam here, that we tried to get the drawings, and the French built the dam, and they don't have the drawings. They took them with them. And we had to pay for them. If we wanted them, we'd have to pay for them. So there's issues, okay? Then those are things. And then any safety inspection reports. Now in California, under that Oroville Dam, there's lawsuits. They're suing the consultants. So you have some responsibilities. If you're licensed, you have the responsibility. That's why you don't lie. If they would have said the drains are plugged, better to err on the wrong side than on the right side than on the wrong side. They forgot. They forgot the drains are plugged. And then any other like flood conditions. And this is just a list of about 10 things that you need to understand how a dam is performing. Well, I'm also doing a lot of instrumentation, and one of the biggest problems we have is that where's the dam data? Who's looking at the data? Now, what I'm worried about with AI, they're going to say, "Oh, AI will do that. We'll just fly it and take a look and finish." Okay, but who went out and looked at it? Nobody. I'm sorry, but your eyes can tell a lot more than AI can do. You can see something that doesn't look right. You know, like I said, in California in 97, 98, actually started in 95, but 97, 98, visual inspections. You're a half a kilometer from the dam levee break and you hear, "What's that water running?" Uh-oh, and it was a break. I watched one farmer cry because he just planted $1 million of strawberries. Central, he lost all the strawberries. $1 million worth of damage. Anyway, but now with LiDAR, all these things, this aerial photography, of course, now, but I'll show you some drone footage of where we're at on the on using drones now to monitor progress with you can actually add LiDAR, and LiDAR is accurate to 1 or 2 millimeters. That's the accuracy of LiDAR. But how do you transmit that? And so using building information, BIM, you can now log all that data into your BIM model, and you get an as-built drawing at the end of the deal. That's really nice. The Corps now is requiring that on all dams. Everything has to be done by BIM. And here, Chibiet and Chijiri, they're building out here in Cheryu, also are you also using BIM to monitor progress? You can do a lot. I'll show you some examples. So Pacific, again, as a geologist, logs of borings, test pits, trenches. These things are all you can find out so much information. Geology maps. We looked at one dam in southern Central Valley, and the problem with that is the sediment coming out of the mountains was so high. In 1995, they had a flood event down in that area, and it washed 5 million cubic meters of soil down into it took out a bridge span on I-5 freeway, took it out. 7 people drove into the dark off the span was gone. Finally, the state police got there and closed the road. So we had to build a dam, a sediment storage dam, 35 meter high. We designed it. Then we started looking, we said, we're building this on an overthrust that experienced in 1988, 4.5 meters of displacement. Oh, not good place to build a dam. So we had to make it a flexible dam, the crack stoppers. So there's some examples of that. So all your materials, like at Chibia Dam, they're going to use RCC, roller compacted concrete. Good area to get into if you're to study concrete. We worked with ITB out of Bandung on the quality of the rock and also the mix design. And we hired an expert from Pakistan and China to help finalize that design. So it was quite interesting. And then when you all reports, you have lots now with the dam center. I don't have anybody been on the dam center? You should try to look it up. I don't have the link with me right here, but it might be interesting if you want to study dams and get involved in dams. There's another book here, Besar di Indonesia, Bendungan. Okay, look at it. It has all the hydrology, all the dams, 400 pages, but it's not updated since 1995. So I don't know if there's a new volume out or not. So you got new dams now, and things have changed. So with climate change, we got to worry about the hydrology. So again, anything else that could come up. And then I've walked many kilometers on dams in all kinds of weather. When you walk on top of a dam and it feels like a waterbed, you may have a problem. Okay. I'm Kedung Uling down central Java. Walking along the crest, there's a crack in the crest of the dam over 1 meter deep, 25 millimeters wide, went down into the dam. So we fixed that dam under DOS 2 because it had a small slide. It continued after the DOS 1. They had to rebuild it again. We put a filter blanket inside to drain it out. So these are things that you look for. Seepage. I walked in one dam in India, and it sounded like there was a river in there. What's that noise? It's a masonry dam. We're 80 meters below grade. And I'm going, is it safe? So they had a bucket. They had a drain there. It was draining 200 liters per minute. That's where the noise came from. And to make it even better, even in the United States, Pine Flat Dam in Central Valley, California, Sacramento, it's a Corps of Engineer dam. They had the same problem. But that's where they came up with some unique designs to stop the leakage, and it worked very well. So these things that if you're observing, you'll learn. I encourage in the civil engineers to get out, get your feet dirty. Get your hands dirty looking at this stuff. Like I said, 2 years behind a drill. You spend some time in the field drilling, right? Yeah. So, but it's okay. It's okay. You get into it, you know. Here it's just hot. There in California, it was hot and cold. With snow sometimes. Second one, again, what do you find in the foundation? Like you saw at Teton Dam, they didn't grout the vesicular basalt. That lava flows are very flat. In central Oregon, there's 7 different lava flows. And how do you build a dam on that without doing corrective work? Okay. Even Glen Canyon Dam and Hoover Dam, they had to go on the abutments and do grouting, because when they did their test fill at Glen Canyon, why is the water coming out downstream 1/2 meter at the same level as the water? It had gotten flown through some cracks on the left abutment and came out. So this is very, very important and also kind of scary. What did we forget? Uh-oh. So, and then never make assumed high strength parameters in a stability analysis not justified or supported. This is where you cannot lie. You have to be honest. Don't base any decisions on assumptions. Where's the data to support it? And then, like I says here, the bottom one, sometimes the owner will say, hey, we just want to just pass it. Just pass it. It's okay. Okay, it's okay. And then something happens. And who signed off on it? You did. So geologic investigation, that's my background on this, is that how do you, not only do you want to look at now with software and hydrogeological software you can buy, it's very helpful. It's very helpful to utilize this information. And then I just have some other comments in here. And then one of the things that Chibia Dam, when they changed from embankment, which you're going to get from the upstream reservoir area, they have to import all the gravel from local, some as far away as 125 kilometers away. So these are problems, and your cost goes up. And then preliminary, rehab, and final. These are the reports that you put out. So I did a lot of the preliminary and also rehab and final reports. We closed out 223 dams in India, and we wrote reports here on 151 dams in Indonesia under DOAS 2. Quite interesting. And then we had to come up with a risk assessment, residual risk, which I'll talk about. Again, I won't go into this, but borings are practical. But remember this. Before you go out and drill a hole, do a geophysical scan. Then you'll know where to drill. Then that's your ground truth. I don't trust geophysical either, like AI. You need ground truth. And I did a lot of this in the government. What is real out in the field? Don't make assumptions. And that's why I say geophysical observations are only good a little bit. Down here, this is laboratory testing, and also it's another good area to work in. And when you hit these samples in the field, what do you do with them? They have to run to a lab and get to know how to do laboratory tests. In soil mechanics, anybody take soil mechanics? Yeah, so you did? Okay, you're a geotechnical engineer, right? Yeah, good for you. Yeah. Study those lab reports on confined and confined pressures. What happened? Because in real life, like at Cheviot, we had to go into foundation and do grout tests. What's a grout take? How much grout is it taking? Where's it going to if we're losing it? Okay, you want to make sure all the cracks are filled. You don't want cracks where water can come. You want that foundation good. So all these tests are good. I got examples here. If you put too much pressure, you can hydrofracture your foundation. When you're putting instruments on a dam, it's scary because you got to use preferred drilling is the auger type, but no slurry. Why? Because a slurry can if you have high pressure with a high dam, you could create a problem, a void, and you could crack your foundation. So these are two important things. So these are the, just to sum up here, seismological studies. Where are we? Where's the closest earthquake? Under DOS, I looked at the new earthquake maps that they published just a couple years ago. And we looked at where our dams are located to see what impact they had on the safety of the dams. And also what geotechnical processes are there. Are we building on an overthrust fault, or are we building on a good solid foundation? But remember, even granite can decompose under water pressure. In California, there's a lot of decomposed granite. DCG, the term we use, and we find, and it just turns into sand. And of course, limestone has dissolution problems. This is liquefaction. I showed you the example for San Fernando Dam failing under liquefaction and overtopping. This is the pictures here are overtopping, what happens during overtopping. A good, if you want to take a note, Dr. David Froelich, he's a water resource engineer, worked with us in India, and he also does a lot of research papers. He developed, you'll see Dr. Froelich's name and formula for how long does it take a breach to form in an embankment dam. He's the one that wrote the formula for that. So if you look at the literature, that's the formula you use. He actually built a small dam. He had money, research money. They built an embankment dam, and they monitored it with test equipment and see how long did it take to overtop in a road. And then when you submit everything, these are all the things that you have to, main things you have to put in your report. Like Passerat Dam, the one that failed in France. Okay, the left abutment, bad, had blocky rock down inside joints, everything else inside. So that was a big problem there. Big problem. They should have found that. They knew it. They were warned, and they said, that's okay. It'll be okay. Not okay. These are just some illustrating material in the report, photographs, map of rock. I think for dam owners, it's important that they also have a person on the team that is also witnessing everything, because you got to get them to sign off on it. I would suggest that the dam owner also has to be involved in this study, highly involved. Just some other thing. This is an example of a downthrust fault under a dam in this is Oskil Dam in eastern Ukraine. I visited a couple years ago, and you can see they built the dam 1955, and it's sitting on top of a down fault. Okay, normal fault right there. See that? Look how much offset it is. They built it, but it's only a small head dam. It's only 16 meter high. So now what are you going to do when they go back to fix it? They have to fix the dam. What do we do? So that's going to be another project coming up after the war ends. So But it depends on the material. On top, there's a site class, how you classify the material underneath the dam. Hard rock, very dense, stiff, soft. Okay. Then under static stability analysis, you look at this, you want to make sure it's safe against overturning and any sliding or sliding of the dam. So what kind of stress is it putting on it? After I spent 2 years in the field, I spent another 2 years doing seep analysis on embankment dam, all the embankment dams in California. So I learned a lot about seepage. You have to build your model. It was a very good program called Fast Seep. Now they've modified it as part of GeoStudio now. Seepage analysis, finite element mesh, FEM. You design your materials. If you have good data, good. If you assumption, no. And then under dynamic, it's similar, but I use the Corps of Engineers has a good program, HECRAS program. You can put in your water, and it will tell you you can run your foundation stability and site under seismic issue. I think here, I don't know if they have. I didn't have a. They have a size. They use it as seismic evaluation, but it's not standard. So we're doing risk assessments. We didn't have good data on responses on how the dams behave under seismic condition. I know one dam in Sumatra, during they had a mag 6.8 earthquake there, and when we visited it, the conduit through the dam they did it wrong. When they built the conduit in the center core of the dam, they modified the soil underneath the conduit. On the upstream and downstream side of that, they did not. Then they put the concrete. So when an earthquake came, guess what happened? The downstream, the upstream side settled about 20 centimeters. Uh-oh. And the tower lost all of its doors. And when I look at there's something wrong with that tower. It's not vertical. It actually settled a little bit. Didn't fall down, but it settled. So how do you fix it? Now you've got big problems, right? So these are issues that can come up when you're doing your investigation. This is the best tool a civil engineer can have. Anybody here use a Schmidt hammer? You have? Anybody else? Yeah. You like? Well, you have to hold it vertical or perpendicular. Yes, right? It's one of the best tools you can use, even on rock. I actually did it on our office building in India at the old library near the Ministry of Water Commission. I tried it on a column, and I tested the column strength, compressive strength of the column concrete. It penetrated all the way. I said, we're living in here, working in here on the 4th floor. It just punched a hole in the wall. Very scary. But this here, this is online. All these references you can find online. 1110-2-2002, Corps of Engineers. They have some really good guidance in there. They're really interesting to have, along with ICOLD. This I brought this slide in because I wanted to show. I had some examples of beam cracks here, and there's just 4 of them. And what happens under compression and tension, buckling, and also crack. But on the right side, take a look at that. You see what you see what's happening? Can you see? Is it obvious to you on the column? What do you see? 2 shear cracks, 2 of them. This is a column in Ukraine. I want a dam, Rahubat Dam. Almost failed. Only the thing on together is a rebar. Thank God. When I worked in Afghanistan for 4 years, but one of the things, they had old Russian drawings for everything. The Russians did all the a lot of buildings, a lot of bridges, a lot of dams. And what we found is that everything they do, they triple. So the factor of safety is very high factor of safety. Quality, not so good. The factor of safety when they design it, overbuilt. So where you might have a 20 centimeter wall, they build it 1 meter, 1 meter thick. Okay, because that was the way they did things. So it wouldn't fail no matter what, assuming that there's going to be no maintenance. No, but we've moved out of that now. This is another damage. The right-hand photo is a compressive failure from an ordnance going off. And that's what it shoved, this 2 meter thick concrete wall. Compressive failure. On the other side, tension. It was all cracked. Unbelievable. How much? That's a 500-pound bomb. You don't have that here, hopefully. But it's interesting to note that even an earthquake can cause this kind of damage. Okay? You look at the failures now on structures, concrete structures, that's scary how we design things. Hydromechanical, I was in Sacramento, California when this happened. I just been there a year, and then this gate failed at Folsom Dam. Unfortunately, it was the high peak flood season, and downstream, about 6 miles, 6.5, 7 miles, there's another dam, the Thomas Dam, a low head dam, maybe 16 meter high, and it has 20-some gates. They had to open all those gates, allow when the water came through here. I have in the notes, I can't remember how many cubic meters per second, quite high. And the stupid thing is on there, if you never get in upstream in a rowboat or a motorboat when a gate is broken or it's spilling. Because what happened is these, one of the TV stations, they hired a boat to take them up to show this dam, this broken gate from the reservoir side. Okay, and what happens? The motor quit on the boat. And one of the guys didn't know how to swim, but one of them was a good swimmer. He jumped out. They left the camera, and there's actually on TV news. You can look it up. The boat went through the spillway and went down 80 meters and hit the deck. Can you imagine? You don't get ever upstream when it's spilling. A dam is spilling. You don't want to be close. I don't care if there's a log boom, something goes bad, you're stuck. Unless and they were swimming for their lives because the current was moving downstream. They got out safely. But this was another issue on maintenance. They had conformed to the new environmental standards on the grease. They used environmentally friendly grease, not petroleum based, and on the trunnions. And when they investigated the trunnions that hold this gate pivoting, they said, all the pins were completely corroded, rusted. All that because the water had washed out all the lubricant. It was water-based lubricant. Oh. And so what happened was one side he was lifting it or closing it. No, he's lifting it, and one side froze, and he didn't see it in time. He said, "Oh my God!" It came unhinged. I saw this happen in India too on a dam, about 4:30 in the afternoon on the 30th of November of 2019. And the next day we had to go down there and find out what happened. Again, those gates were 60-year-old gates, and guess what? How many know what organic corrosion is? Anybody? Organic corrosion? The gates were 60 years old. They'd been subjected to poor water, and they found the gate skin was supposed to have been 10 millimeters thick. It was 2 millimeters thick. But nobody had checked thickness of the plate. So they had put in brand new bearings, trunnions on these gates, but nobody checked the plate thickness. And a log or something came down, hit it, smashed it. Fortunately, they had the emergency action plan in place, and so nobody was hurt. It was a small, but then they had to go back in, fix all 8 gates. All 8 gates were in the same condition. Organic corrosion, look it up. For chemists, it's a good one. I'd never heard about it until then. This is just when you're looking at how do you set up and what are you trying to do here? And a lot of it you're going to be strapped by the dam owner because I have no money. I don't have any money for maintenance. I don't have to be careful. So I don't want to do everything. So what do you have to do? So this table just shows you how you would scope and cost out an investigation. And don't go cheap. Never go cheap. Okay. Don't be the low ball. No, you go by experience and your reliability. How good are you, and can you make sure the dam's going to operate safely? Yes, it costs money, but it's in the end, it's worth it. Just a summary, preliminary investigation. Usually that's desktop. Did a lot of desktop before we'd go out in the field. In India, we looked at every dam, but when I get here, I looked at that Besar di Bendungan Besar di Indonesia manual. I said, okay, I made copies of the cross sections, hydrology. Then we'd go visit the site, and then come back with our assessment. And what happens here? A rehabilitation investigation, and then final investigation, enough for construction. And then here's an example under DOS of this is BBWS Pomale Juana, and we looked at the dams there. I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, yeah, 10 dams. And the red is the QPMF, and the blue is the Q1000. When you build a dam now, you're supposed to design for for PMF, but there's I'll say, a way out. If it's already designed, built, right now they're just going with the Q1000 hydrology, 1,000-year hydrology. And so you can see most of them pass the Q1000, but look at the Lodan, Simo, and Banyakuwang. Look at the PMF. Okay, can't handle it. So, and Lodan, which is a good dam to study, it actually had a small failure under another earthquake where the foundation liquefied or settled, and they fixed it. Okay, so they had to go back in and they had to put an upstream filter and under drains, under other things. So, but it was an interesting dam to study. And Simo is a small dam. They fixed that by building a higher under rehab. They did that one by fixing the retaining wall. Then you have to this is where it comes important. Here in India, you have to license through the DSC, the Dam Safety Commission. And so you have to go through your preliminary. This is the 40 dams we had in Central Valley, the Central region. And how many, what do we do here in process? You can see that we had to give a lecture to the DSC on how that dam is performing. Hydrology, structurally, everything, all the and social, environmental, all these aspects have to be covered under dam safety. Very, very exciting work. And but you had to prepare. You had to have your answers. This is something that I spent I came here as a dams instrumentation engineer under DOAS 2, and they assigned me to do the risk assessment, to modify the risk assessment, make it more handy. So we built a SQRA, and that's still I don't think it's yet published, but it's at the BTB, JLA Technical Meeting, to be completed. That will help. What that will help is it will assess how you categorize the dam. And you can plan for any major rehab work. So we looked at the assessment of 151 dams for all in Indonesia. And after their work was done, we went back and we saw what residual risk were left. So I think under DOAS 3, which will come out when it gets some money, when the government gets some money, DOAS 3 will be ready to take up any leftover remaining risk that have to be still there. So very interesting concept. It's a good, they had used I-code, the modified I-code. We went with the current I-code information. And in this, I have a bibliography that has all these references in it. Please avail yourself and try to get interested in it. I wish that, do they have dam safety training or dam safety construction in the universities here? I don't know. Do you have it at your school? No? No? Okay. I leave you with this. This was, can I play this? Can we play this, YouTube? Can you play this? I'll leave you with this, then we'll answer some questions. This is the copper dam that my mentor, Clark Stanage, worked on. Auburn Dam, copper dam upstream, so they could build their conduit. Yeah, turn the sound up. Turn the sound up. Uh-oh. Now what? What? Do we have sound? Sound's off.
North of Sacramento, California, on the American River, Auburn Cofferdam was built in the early 1970s. It diverted the river flows around the construction area for the foundation of the proposed Auburn Dam. The earthen cofferdam was modified in the late 1970s. At that time, a safety plug, a soft plug, was built into the right abutment, and the remainder of the structure was raised 8 feet. The plug was designed to erode if the capacity of the cofferdam was ever exceeded. This would allow the dam to fail gradually and the stored water to be released over a period of hours. This slow breach would also restrict the amount of the embankment material entering the river. Downstream, Folsom Dam and Reservoir was operated on the assumption that Auburn Cofferdam would fail if its capacity was exceeded. For computation purposes, the water stored behind the cofferdam was added to Folsom storage. California's unprecedented storms of February 1986 resulted in large inflows that exceeded the diversion and storage capacity of Auburn Cofferdam. On February 18th, the safety plug in the right spillway of the cofferdam was overtopped, and it began to erode as designed. The erosion of the spillway and drainage of the reservoir behind the cofferdam occurred over a period of about 12 hours. Bureau of Reclamation personnel videotaped and photographed the failure beginning at about 6 a.m. and continuing until late afternoon on the 18th. The erosion of the safety plug was essentially completed by about 3 p.m. The following footage is a chronology of the designed breach of Auburn Cofferdam. The cofferdam was functioning properly before the flooding occurred. From these views, you can see some of the foundation work that had been completed before the Auburn Dam project was stopped several years ago. These shots were taken beginning at about 6:30 a.m. on February 18th. They show the overtopping and the beginning erosion over the spillway plug. Downstream from the cofferdam, erosion is starting to take place along the edges of the spillway channel. At this time, some erosion of the spillway plug has probably occurred. As the time progresses, more erosion takes place. Note the elevation of the water behind the cofferdam in relation to the road on the left abutment. As the plug continues to erode, the water level behind the dam will drop. The flow is now sufficient to start erosion on the edge of the spillway canal downstream from the cofferdam. Quality dam downstream had previously been breached for other purposes by earth-moving equipment. In the spillway, the erosion is horseshoe-shaped as it progresses upstream toward the spillway plug. A short time later, the horseshoe-shaped erosion has gained momentum. The diversion tunnel is discharging below the previously breached water quality dam. Massive erosion along the downstream edge of the spillway channel is beginning to take place. The water eats into the toe of the dam. Huge chunks of earth begin to crumble into the flow. The spillway dramatically continues to erode. A distant view shows the spillway channel erosion. Significant erosion continues on the cofferdam. Downstream, the diversion tunnel continues its discharge. A swirl forms in the cofferdam reservoir at the intake for the diversion tunnel. The horseshoe erosion near the left side of the channel continues to move upstream. A substantial quantity of earth is being moved by the large flow of water. As the water eats further into the structure, the pace of the erosion speeds up. The erosion has progressed through the entire spillway channel and is starting to move back to the plug. The spillway erosion has moved back beyond the access road. The flow through the spillway channel and the erosion continues to increase. The erosion on the right side of the channel has almost reached the safety plug. It is now noon on February 18th. From a helicopter, we get a different perspective as the erosion nears the plug. The flow is substantial, and the elevation in the reservoir is still near its maximum. Now, the first stage of erosion has reached the plug area. A second stage is moving back towards the spillway and the cofferdam. The water elevation on the downstream face of the dam is rising very rapidly. This indicates a much increased flow through the spillway. The reservoir elevation is still close to maximum. The breached water quality dam and diversion outlet as they looked from the air. Because of the backwater effect of the high flow in the channel, the discharge through the diversion tunnel has probably decreased. The erosion in the spillway continues at a significant rate as the downstream water surface elevation continues to rise. Now it's about 2 p.m. The erosion has worked its way into the reservoir area and the water surface elevation begins to drop at a substantial rate. Upstream from the reservoir, the heavy flows have forced a log boom to break loose, and the debris in the upper part of the picture moves toward the spillway channel. The erosion continues in 2 stages. The level of the reservoir drops and the flows become greater. The debris of logs moves into the opening. Downstream, the water elevation continues to rise, while in the reservoir the elevation has dropped substantially. This is the situation about 2:30 p.m. on February 18th. 30 minutes later, at approximately 3 p.m., the erosion of the safety plug was substantially completed. All of the water in the Auburn Cofferdam Reservoir flowed downstream into Folsom Reservoir. This effect had been considered prior to the Cofferdam failure, and space had been reserved in Folsom. Here, on February 18th, the discharge through the spillway gates at Folsom was approximately 130,000 cubic feet per second. Nimbus Dam, which forms an afterbay below Folsom, was also discharging 130,000 cubic feet per second. This was 15,000 cubic feet per second greater than the design flow of the floodway downstream. However, the floodway levee held. On February 19th, the day after the breach, this is what Auburn Cofferdam looked like. Downstream, you can see the sedimentation on the left side. If you look closely, some of the foundation work can be seen in this upstream view. Again, Auburn Cofferdam the day after the breach. Though Auburn Cofferdam failed, it did so by design.
I only show this to give an example of, this was designed maybe not at the right compaction. When you design this, it was made out of erodible materials like silt. Finish. Yeah. Yeah. Okay. Yeah, I think just see going there. Oh, here's a list of references I put in here. That's why I want to share this with you guys. And the book on the right, I haven't looked at it in a couple of years. Maybe, boy, what a good encyclopedia of your dams here in Indonesia. I encourage everybody to take a look at it. Good stuff in there. That's it. That's all I have. Now, wait just a minute. On the Copper Dam, my boss, my mentor in Sacramento, Clark Stanage, he worked on that. And that dam was going to be about 200 meter plus high. And the environmentalists killed it because of some fish movement and salmon going upstream. But also, technically, does anybody know what RIS means? Reservoir induced seismicity. If you have too much water, high head of water, what happens in the foundation? And if an earthquake comes and it's porous rock, guess what? You've now shaken up the foundation. So that's how it got killed the last time it got killed. It was finally killed nine years after that Copper Dam failure. They kept trying to build it. They ran into all kinds of problems. California, being California, it's they stopped it. So, but I do, if there's any chat questions, and if I can't answer anything, I'd like Rifa. Where'd we go? Oh, can you send me? You have my email. I can answer any chat questions. Okay, but do we have any? Sure.
Can I just say that if anyone has a question, can you read the question first? Because it's not easy to hear the people in the back of the room, or give them the microphone.
Thanks, David.
All right, so anyone in the room, do you have any questions? I can see the room is fuller now. Welcome, everyone. Also, thank you, Ed, for your excellent presentation. So anyone, this is a Q&A session. If you have any question, you can raise your hand and Ed will be happy to answer your question. Also, for those who are joining online, if you have any questions, you can use the Q&A feature located at the bottom of your screen. So you can just submit your questions and Ed will be happy to answer your questions. So anyone in the room? Do you have any question?
Come on, questions. Okay,
Yeah, sure.
one hand up.
Okay.
Hi, sir. I want to ask to analyze the failure of the dam in Indonesia, how advanced I should take fluid mechanics or fluid dynamics course?
Can
How advanced should I take fluid mechanics course to fully analyze the failure of the dam?
aha, if you have data and not assumptions, right?
Data and assumptions.
There's good software. I'm trying to learn Praxis 3D right now, which is very hard for me. Okay.
Should I take numerical analysis as well?
I'm sorry.
Should I take numerical analysis as well?
Yeah, yes, numeric analysis, yes, yes. And that you have to have some data, field data. And do you have that data?
No, I just wonder if can you plot it in computer program or run it to program so we can run the program without any data or any assumptions.
You can make some assumptions and run it. And based on the book encyclopedia, which tells you all the kinds of dams, the Besar, Bendungan Besar di Indonesia has all the parameters you need to run a first one, but that's old data. And how accurate is it? You don't know.
I don't know.
So yeah, so I would say that you can do it. You can study on GeoStudio. You can run HEC-RAS. You can do Praxis 3D. And the software now is changing so fast for me that I'm having trouble. I won't say, I'll only tell you guys this, haha. I study engineering with a slide rule, okay?
All right.
But remember this, they sent a man to the moon using a slide rule, okay? So it works, just slower, okay? So, but I think I would learn the software programs that you can use now for doing this work. It's very, very progressive. Software now is, but what I'm afraid of is that it'll get so good that there won't be any human input into it, only AI.
Are you using AI to run the program or what?
They're working on that. Yes. Yeah. Everything. I don't know what we're here for. Us old timers, we don't have to worry about it. You young guys, I don't know.
I see.
Yeah, but yeah, learn these software programs because again, AI is not eyes. There's no eyes in AI. Okay. Okay.
Okay, thank you for your time and
No, I
suggestion.
love this. This is good.
Okay, Ed, can I just add something if you can hear me?
Yeah.
I think most of the major dams in Indonesia have been subjected to a dam break analysis, which shows what happens when the dam fails in different ways.
Yeah.
In fact, I use the dam break analysis for Jati Lahore to look at the depths of flooding downstream because a certain developer wanted to develop an area and he wanted to know what the risks were.
Yes. Yeah.
And whilst there were no ordinary river flood risks, their site was covered by the dam break analysis.
Yeah. Look, and that DBA, that dam break analysis, is important for, first of all, that's one thing I was waiting for at Chibia is that we didn't have the floodplain mapping downstream because you have to have that for your emergency action plan. And so where are people going to run to when the dam breaks? And most of that land downstream of Chibia and the Chibia River is rice fields and flat all the way down to a small weir which would overtop. So that's but that's critical. Your dam break analysis is very critical to calculating the risk to people. Like you saw on Oroville Dam, 200,000 people evacuated. 200,000. And they came back 12 hours later. They said, okay, come back, but there's still risk. They thought, okay, it's not going to collapse. By that time, the rain had stopped and the inflows had slowed down enough. so that they were able to control it. But that just tells you how important it is. If you don't have your emergency action plan in place, that's why the floodplains are #1, dam breach analysis. Embankment dams break differently than concrete dams. Okay, remember that also. There's too many dam breaks on YouTube. I've studied them for years and they keep getting better, but at some point I get tired of looking at them anymore, because how well do you design a dam? You want to you don't want to make it so expensive it becomes like a Lamborghini, but you want to make sure that it's safe for the people that live there. Not only that, the other thing you have to watch out for is what they call creep and safety, dam safety creep, risk creep. If you build a dam, people say, oh, I can build my house downstream here and I'll be happy. It's not gonna fail. I don't want to flood anymore. Well, you better look at that. Because if a dam breaks, your safe house is not safe anymore. So it's important that everybody have that in their mind. And so that's why we ask the BALIs, the dam owners, make sure that you don't allow industrial or airports or high population centers just downstream of a dam, because there's always going to be a risk. Always. David, did that help?
Yeah, I think so.
Yeah.
I would just like to add that you also have to consider climate change, that you can't use historic hydrology data to predict future risk. We did analysis of all the north flowing rivers above JLA, including Chibit, and we found that we're in a 30-year advanced period. Flooding could increase by something like 30 to 40%. The flood discharges, the floods coming into the reservoir could increase by that amount. And that's just in the next 30 years.
Yeah, and now downstream on the Chibit, down near that weir, population and the industrial zones now have been built up in that area. And I'm worried about the impacts of any flood down in that area based on what happens if the dam breaks. So those are going to all go all the way down to the JLA River, right, David?
Yeah, correct.
Yeah.
Well, it's the Chitterum River.
Yeah, Chitterum River, yeah. Water discharge from the JLA Dam, yeah. Which is another story. Okay.
Okay. So I think because we're running out of time, probably the last question from online attendee. There's Alan Sullivan asking, is it possible to incorporate early safety warning devices into dam structures? Is it possible to incorporate early safety warning devices into dam structures?
Absolutely. As an instrumentation specialist also, this is telemetric monitoring and performance of your dam during heightened flood season. Also, it's your early warning system. I notice here they don't use sirens too much. India, your siren has to be heard 5 kilometers away. Quite loud. I tested one time and I was on top. I said, hit the siren. My God, I thought my ears were gonna break. So but it has to be able to hear downstream. And you can incorporate that into your telemetric monitoring when your piezometric pressure may get too high, when your seepage increases, and your rain forecast. One of the things they're trying to do is improve weather forecasting. Under DOAS, we have funds for doing that, changing the radar, better radar to map how much rain is anticipated in that watershed. But it's expensive. It requires new radar systems to be put in place. So, does that help?
Yeah.
Also, emergency action plan has to be in place.
All right. Okay, I think because of the time, we have to close the Q&A session. But anyone who still has questions, you can ask at probably over dinner after this. So everyone, once again, give a round of applause for Ed Flint. Thank you, Ed. Okay, ladies and gentlemen, we have now reached the end of the event. Once again, thank you for your participation, whether you're joining online or you're here with us. And we hope we can see you at the next event. At last, good evening and stay healthy, everyone. Thank you.